Hello, welcome back. We are now in our second video for Chapter 5, and let me introduce the concept of vapor pressure. So the idea is kind of like the pressure that a liquid exerts on the surface. See this picture here, you have liquid water, and it's like there's a pressure that's being pushing up on the surface of the liquid. And the idea is that when the vapor pressure equals the ambient pressure, then the liquid boils. But at the same time, that vapor pressure is also the fraction of gas in the liquid over the where the vapor pressure is the fraction of gas vapor over that the liquid. Well, fraction I mean by pressure. So if the vapor pressure is 50 millimeters of mercury, that means the pressure in a sealed container will be 50 millimeters of mercury, or whatever liquid that is down there. And here is the vapor pressure for water at various temperatures. If you go on to engineering, you will learn all about this with the steam tables. I've had to use that lots and lots of times in my engineering pursuits. So don't worry, engineer and a chemist. Okay, so let's look at an example to illustrate this issue. In order to determine the rate of photosynthesis, the oxygen emitted by an aquatic plant collected over temperature of 293 Kelvin, total pressure of 755.2 millimeters of mercury. Over a specific time, 1.02 liters of gas is collected. What mass of oxygen in grams is formed? So you look at this chart here, 293 Kelvin minus 273, so that's 20 degrees Celsius. So, and that means the vapor pressure is 17.55, as shown by this chart right here. And let me show you this picture. I guess I should have talked about this picture. Here's my beautiful, no happy little clouds here, Bob Ross fan. So the idea is we have an aquatic plant, probably algae, in a vessel, which is probably just an upside down tube, and over it you have oxygen, and since this is liquid water here, so we have the liquid water here, you're going to have water vapor alongside the oxygen. So that means that the pressure total is the pressure of the O2 plus the pressure of the water. So, which implies the pressure of the pressure of the water, the pressure of the O2, this pressure total minus the pressure of the water, which is 755.2 minus 17.6, and that equals 755.2 minus 17.6, 737.6. Wait a second. I guess, yeah, 12 months. 737.6 millimeters of mercury. Okay, so then, so we need the mass of oxygen, total pressure, the temperature. So we need moles. PV equals nRT, which implies N equals PV over RT. And then we take the number of moles multiplied by 32 grams per mole for oxygen. So pressure, 737.6, atmosphere over 760 millimeters of mercury, volume 1.02 liters, all over R, 8.314, that's different R, different unit, 0.08206 liter atmosphere, mole Kelvin, temperature 293 Kelvin. Okay. So then put the numbers in a calculator, you get 0.04 moles oxygen, and then multiply by 32 grams per mole, and that's from the periodic table. If you don't know where I'm getting 32 from, O2, you have the periodic table, and if you look look at oxygen, actually then here it's 16 grams per mole times 2, 32. Okay, now let's look on to some things that are more important. Methanol can be synthesized by this reaction. Carbon monoxide plus 2 hydrogens makes methanol. And that is, in fact, how we get methanol, one of the good ways we can do it. What volume in liters of hydrogen gas at a temperature of 355 Kelvin and a pressure of 738 millimeters of mercury do you need to synthesize 35.7 grams of methanol? Okay, so if we're doing this for real, this would be a much higher temperature, probably at least 1,000 Kelvin. And a pressure of, it wouldn't be close to 1 atmosphere, it'd be like 100 atmospheres. So that's the way we do it in this industry. And we wouldn't be making 35 grams of methanol, we'd be making 35,000 tons of it. So this is something I guess you're doing in a physical chemistry laboratory. It wouldn't be like this at all. The other thing to note, this right here, carbon monoxide plus 2 hydrogens, this is known as synthesis gas, or syngas, or also has been known as town gas. So this is what is used to make a lot of things. So do I mean like a lot of things like hydrocarbons? So if you know your history, so in Nazi Germany, one of the easiest things that the Allies try to do is like, well, let's limit the amount of oil that Hitler gets. In the United States, we did this also to Japan. Before Japan attacked us. In the United States, we still have lots and lots of oil, and we are a huge exporter of oil, and we give Japan really, really small amounts of oil. So fuel was a big thing in World War II. And a lot of the strategies, like one of the pushes Germany had was going for the oil fields in Stalingrad, and that's where they were stopped. So they were trying to reach the oil fields, for instance. So fuel was a big thing in World War II. But Germany at the time was the most technologically advanced nation, and so when Allies tried this strategy, let's stop giving Germany oil, what did the Third Reich do? They used their chemists to do what's called the Fischer-Tropsch reaction, where you take carbon monoxide and hydrogen and it makes synthetic fuels. And in many ways, these fuels are better than the fuels we use today. We still have the petroleum-based fuels. They burn very cleanly, and they're like, if you look at gasoline, it looks kind of like apple juice. The fuel coming from synthetic fuel plants, it's clear. It looks like water. And they used it as jet fuel, so it was low octane. It was more like diesel fuel. They use that in their airplanes and tanks and whatnot. So, and the miners, the coal miners preferred the synthetic fuels as well because they didn't smoke as much. So, more history. In the 1970s, there was South Africa instituted a series of laws called apartheid, and where it was basically segregation due to race. Well, I shouldn't say race by color of skin. There's only one race, human race, of course, but by the color, what we contemporarily inaccurately call race. So so what did the world do? An oil embargo against South Africa. What did South Africa do? It's like, well, you know what? Technology has been around since the 40s. Let's make our own fuels. And they do, and they still do. And there's a company called Sasol that does this. They make their own fuels. In the United States, we're trying to do this as well, because we're trying to we could break oil. We could get away from it. We just make synthetic fuels. But we have hundreds of billions of dollars of infrastructure built up towards petroleum. So that's an issue. Anyways, so politics, if you haven't noticed, politics and chemistry are very, very mixed. So let's do this problem with synthesis gas making a little tiny amount of methanol. So this is how much hydrogen gas do we need to synthesize 37.5 grams. Okay, so we need the number of moles of hydrogen. And from that, we can get the volume hydrogen. So, okay, so we need, let's do dimensional analysis, 37.5 grams methanol, CH3OH, Carbon is 12 and 3 hydrogen, well, 4 hydrogens. 4 hydrogens plus 16 for oxygen. Let's see here, 4 plus that's 32 grams per mole. Mole CH3OH over 6, oops, what did I say? 32. 32 grams per, oh wait, so it's already there. Mole methanol. Always need moles, always need a straight shot just for moles. Hydrogen, that should be easy. Oh, and the other thing, oh wait, and then there's a conversion. You need 2 moles hydrogen to 1 mole CH3OH. And I'm getting that from the chemical equation there. 2 to 1 molar ratio. And let's do this. 37.5 divided by 32 times 2. 2.34. 2.34 moles hydrogen. And now we need volume. PV equals nRT, which means V equals nRT over P, which is 2.34 times 0.082, this is moles. 0.6 liter atmosphere over mole Kelvin. Temperature 355 Kelvin. All over 738 millimeters of mercury times ATM over 760. So now all the units will cancel out, which then equals 70.3 liters, and the calculator is up there for if you want to review later on. Okay, airbag volume. So another question similar. Airbag volume. How much sodium azide is needed for an airbag? What atmospheric pressure, 0 degrees Celsius, to have a volume of 11.8 liters. So one of the questions I get with this question frequently is, how do I know this is an ideal gas problem or a gas problem? Well, you have a volume of 11.8 liters. And well, why doesn't it turn into sodium azide or sodium metal? Well, solids are tiny. We did this calculation last lecture that gases are like on the order of about 1,000 times less dense than, at least this temperature and pressure, than the condensed forms of matter, so liquids and solids. So what fills up an airbag is gas. So so if you've ever been in a car accident, sodium azide is really explosive. You touch it, it explodes. So what they do is they take a bit of sodium azide and they wrap it typically in something that doesn't corrode, like gold foil, and they stick it in an airbag. And the idea is if there's a big impact, it will rupture some. They put it with enough cushioning in it so that if it's hard enough, it'll rupture the container, and then the sodium azide will just expand. The nitrogen will form, expand really quickly, and form the airbag. So, unfortunately, also makes sodium metal, which is extremely corrosive. I was in a car accident once, and the airbag deployed, and I'm a pretty big guy with long arms, so I usually sit pretty far back from the steering wheel. Anyways, airbag didn't even touch me, but I got showered with sodium oxide. Well, maybe not so much in my face; it was on my arms. I've had students that were in car accidents that come and tell me later, like, I breathed some of the stuff in, and it hurt. So it's that's a dangerous thing. So you generally avoiding car accidents, even with an airbag, is a good thing. It's not like the movies where airbag deploys and you stick your head on it and go to sleep. No. If that happens in a car accident, don't do that. You might get scarring on your face from the sodium oxide. I say sodium oxide because the metal reacts quickly in air. Okay, so how do you do this problem? You need, how much is on? So you need moles, NaN3. So we need that, and we get that from the moles of nitrogen. We get the moles of nitrogen from the volume of nitrogen. So PV equals nRT, and N equals PV over RT. And 1 atmosphere is, so pressure is just 1 atm. Volume is 11.8 liters. 0.08206 liter atmosphere over mole Kelvin, and 273 Kelvin. And then you get that number, and then so N2 times 2 moles NaN3 over 3 moles N2, and then you need the molecular mass of sodium azide. So 14 times 3 is 42 plus 23, that's 65. 65 grams NaN3 per mole NaN3. So that's the way you do that. So 14 times 3, that's 42. That's right, 65. Okay. So doing that, you'll get the answer. There's a shortcut here, though, if you want. This is also known as STP, standard temperature and pressure for gases. Actually, standard temperature is 298 Kelvin for everything else for thermodynamics, but for gases, for molar volume, it's 22.4 liters for an ideal gas, or about that, I should say. So if you want, you can take this number and divide it by 22.4. That's another easy way to do it. But I usually just use the ideal gas law. That's just what I always do. So do that, and you can get the answer for that one. Okay, so let's look more into stoichiometry of gases. So here we have methane plus water to form carbon monoxide and hydrogen. So this is in fact how we make hydrogen, or one of the ways. So this is called steam reformation, and I've talked a little about it before. We usually don't make hydrogen from electrolysis, although it says, oh, we should. The only time place we really do that is in nuclear submarines, and you're after oxygen, not hydrogen. So, but this is how industrially we do it. And of course we would use much higher temperature and pressure than what is listed here. But this is a limiting reagent problem. So we have a limiting reagent, and we have methane. We have 25 liters of it, about an atmosphere of it at 25 degrees Celsius. And water, we have similar volume and pressure, but 100 degree more temperature. So, which one is it? Well, I mean, if you look, methane and water are both 1-to-1 molar constant. Like right here is the reactants. It's 1-to-1 molar, and for methane, there's a higher volume, which means more moles, higher pressure, which means more moles, and lower temperature, which means more moles. So just by logic, I know that it's water. Okay, so I can just go and we can figure out how many moles of hydrogen we get from this. We can logically just look and see, reason that it's water is the limiting reagent. So we'll go ahead and do this. So, and we're looking for the moles of hydrogen produced. Like any limiting reagent problem, we're looking for the moles, the theoretical yield of hydrogen, and limiting reagent here is water. So we have to figure out the moles of water. So PV equals nRT, N equals PV over RT, which is 702 atmosphere for 760 millimeters of mercury. Volume, okay, 22.8 liters, and over R, 0.08206 liter atmosphere over mole Kelvin, and that's 398 Kelvin is 125 degrees Celsius. Okay, and that'll give us the moles of hydrogen, and there is a, so then moles hydrogen give us, there's a 3 mole hydrogen to mole H2O, and that'll give us that. Then we take this number, this, I guess we got to do the actual, because that's this theoretical yield, that the number pound sign that I just had. Then we have to figure out what the actual moles of hydrogen are. So actual and hydrogen, this is going to be same thing, PV over RT, but this one here is for that one there. So 1 atmosphere, 760 millimeters of mercury is 1 atmosphere times volume. You can use a 22.4. That's the other one you can do, is divided by 22.4, like I told the last problem. But 26.2, how often you're in that situation is very, very infrequent. I mean, no one would dare do that such a low pressure and temperature in industry in such small volumes. So that'll give you the N actual. So take the number over N actual, and you'll get the percent yield. If you wonder where I went and double checked to make sure that the water was in fact the limiting reagent. So I just verified that. So okay, coming back. Last topic we'll talk about this section is kinetic molecular theory. So, for instance, say you go to somewhere like McDonald's or one of your fast food place of choices, and it'll say like, ask like, you can see nutritional information for things, and you're like, what's the number of calories in a Big Mac? I usually don't eat that, but I looked it up frequently, and I think it says 550. Well, frequently, I think I remember seeing that somewhere, but it doesn't matter. Does that mean every single Big Mac is 550 calories? And the answer is no. But there's some sort of distribution where you have an average of about 550 calories from that Big Mac. And this here is, we're going to build up to as kinetic molecular theory, because not every single gas is going to have the same energy. So when you have a mole of gas, so a big number, like 6.02 times 10 to the 23rd number of particles, and they're all whipping around, and at a temperature, so temperature means average translational kinetic energy, so how fast it's moving in a very Cartesian sort of XYZ fashion. So how fast it is moving with really from, not rotation, not vibration, but motion around in space, translational kinetic energy. And the average doesn't mean that everything's going to have the same energy. It just means, like, it's the average. So you're going to have some going really slow, some going really fast. So here are the postulates that form kinetic molecular theory. The size of the particle is negligibly small. That means the volume is only from the falling gas itself. So what we're building here, this is what the ideal gas law is based off of, and this is the perfect gas. Like, what is your perfect partner? What is he or she like? You come up with some dream model idea. This is the dream model idea for a gas. So number two, that we just mentioned. The kinetic energy is proportional, and the third one is collision with each other is completely elastic. That means there's no attraction. So the thing is if you have two gas particles and they're flying around, but if they're attracted to each other and they form something like this and they dance around like this, now two particles kind of form to like one particle because they group together. So there is no attraction to them. And sparing you the derivation, the root mean squared. So what is the root mean squared? It is the square root of the mean of the velocity. So why do we care? Why do we, first of all, why is it U in chemistry and V in physics? I don't know. We use different symbols sometimes. And so velocity, if you've taken physics, velocity is just like speed, but it has a direction. So you can have negative velocity. So how do you get rid of the negative signs? You square them. Negative squared is a positive. So, and there's no imaginary speed, so we don't have to square I. So squaring the velocity will always give us a positive number, and then we take the average of that, the mean of that, and then square root of that, and you get a value. And the root mean squared actually corresponds to the tops of these peaks that I like so. Okay, so here is the variation of the kinetic energy molar mass, and you can notice that the heavier molecules have a very narrow distribution and the light molecules have a very broad distribution. So light hydrogen at only 2 grams per mole is whipping around very fast, and then heavy oxygen at 32 grams per mole is much more tight. It doesn't do that much. Okay, and then let's look at temperature. So this is nitrogen at different temperatures, and something to notice is that at a cool temperature the distribution is very narrow, and at a high temperature it's very, very broad. So if you look at gases, they're whipping around and they're bumping into each other, and you can have a situation where you have two gases, and this one's traveling this way, and one sneak up can go, and this one can go really fast, and now this one can go really slowly. So you can actually have very cool, at least in terms of speed, temperature, individually for certain molecules or atoms in a gas. Likewise, you can also have some that are very, very fast. But you always have the average, the root mean squared average. So why do we care? Among other things, so when you later on you'll learn about, if you take a second semester, you learn about reaction rates. And paper, if you look at paper at standard temperature, it burns. It burns at this temperature. It burns extremely slowly. Like if you've seen really old paper, it's starting to turn yellow. It's kind of like it's burning really slowly. Well, it is. That's exactly what it's doing. But the thing is at a low temperature, let's say that you need this much energy for the paper to burn. Well, if you look down here, there is a little tiny fraction of gas that has, at this temperature, well, 273 Kelvin, that's a little chilly, but because that's 0 degrees Celsius. But there's a little tiny bit of gases that have enough energy to react with the paper. Whereas at a higher temperature, there's about half of them. So 2000 Kelvin, about half the molecules have enough energy. And so that's going to burn fast. Of course, this is nitrogen. Nitrogen doesn't react with very frequently. But if it was oxygen like in air, you're going to have oxygen's pretty reactive. So that is in part why temperature increases the reaction rate, because you have more molecules that have enough energy to overcome. So in order for things to react, atoms and molecules have an electronic cloud and it's negatively charged. They don't like each other, so when atoms approach each other, they slow down because of the negative repulsion. To have a collision and a chemical reaction, there has to be enough energy to overcome the electronic repulsion. So, if you ever looked at old paper, now you know why it burns ever so slowly. And then you put a match under it and it catches on fire and disappears in seconds. So that's that. So anyways, we will talk more about this next time. And I will see you later.